talk on hyperbolically embedded subgroups. So my main goal for today is to just give you some examples of properties of hyperbolically embedded subgroups and some of the things that you can use them to do. Okay, but first I want to give one more example, which I said out loud on the first day, I think, but I want to write it down. And this is the relationship between relatively hyperbolic groups and hyperbolically embedded subgroups. So a group G is hyperbolic relative to a subgroup H, if and only if that subgroup hyperbolically embeds into the group with respect to some relative generating set, and that relative generating set is finite. So most of the time for hyperbolically embedded subgroups, the relative generating set is infinite. But in the special case that the subgroup is a peripheral subgroup in a relatively hyperbolic structure on the group, then you can choose this relative generating set to be finite. And it's an if and only if. So you can take this as a definition of relatively hyperbolic groups. Francois on the first afternoon gave actually the equivalent definition of a relatively hyperbolic group. He defined it a little bit differently. He talked about coning off the subgroup H in a Cayley graph of G. So like adding a vertex and adding edges from each of those vertices to the vertices in H. And that coned off part, so that construction is equivariantly quasi-isometric to adding H to the generating set S, right? So you're still metrically collapsing it, but you're doing it in two different ways. And then he said that you want this like angle metric to have some properties, and the angle metric, you removed the vertex you added and then looked at other paths through the space. Removing that vertex is like saying you can't use any edges in that copy of the coset that you were coning off, right? Like removing that vertex sort of represents all of the H edges at once. So he actually gave the same definition that with that angle metric, he needed the subgroup H to be a proper space. And the fact that he started with a Cayley graph of the group with respect to a finite generating set corresponds to this fact that S is finite. He mentioned this, there are lots and lots of definitions of relative hyperbolicity. The one that he gave, which is this one, is probably not the one that most people give as a first definition. A lot of people talk about that coned off Cayley graph, but instead of looking at an angle metric on it, they talk about properties of geodesics in that space and like bounded coset penetration, for example. But those are all equivalent to this. And then one other thing I want to say about this case relating to what we talked about yesterday, in this case, so when you have a relatively hyperbolic group like this, the action of the group on the Cayley graph of G with respect to S disjoint union H is always acylindrical. This is not an if and only if. But we said yesterday that generally, if you have a hyperbolically embedded subgroup, it may not be the case that the action of the group on this relative Cayley graph is acylindrical, but in the special case that you have a relatively hyperbolic group, this is always true. And maybe the last thing I'll say is I've taught this whole course with a single subgroup, and I said right at the beginning that you can do this with a collection of subgroups. This theorem and this statement also holds for a collection of subgroups. So Francois's definition of relative hyperbolicity was relative to a collection of all of the cosets of some finite collection of subgroups, right? And this will generalize, but again, you have indices and everything just gets a little bit more complicated. Okay, so that's the connection with relatively hyperbolic groups. And in many ways, this relatively hyperbolic groups were the inspiration for acylindrically hyperbolic groups, and peripheral subgroups like this subgroup H, their properties were the inspiration for hyperbolically embedded subgroups in acylindrically hyperbolic groups. So a lot of the properties that we're looking for about hyperbolically embedded subgroups come from the fact that we already know them for peripheral subgroups in relatively hyperbolic groups. Okay, so here's actually here's one thing you can say about hyperbolically embedded subgroups in general. This is a result due to Sisto. So this conference is talking about the geometry of subgroups. So what's the geometry of hyperbolically embedded subgroups? So how do they sit inside the group itself? So Sisto shows that if G is a finitely generated group, and let's say that T is a finite generating set, and H is a finitely generated subgroup of G. So if H hyperbolically embeds into G, and so here I'm not specifying the relative generating set, so that just means there is some S, maybe finite, maybe infinite, we don't know. But if H hyperbolically embeds in G, then for all constants mu and c, there exists a constant m, depending on mu and c, such that all mu c quasi-geodesics, and these are quasi-geodesics in the Cayley graph of G with respect to this finite generating set. So sometimes you might just say that these are quasi-geodesics in G itself. And let's assume that these quasi-geodesics have their endpoints on H. So all of these quasi-geodesics are contained in the M neighborhood of H. Okay, so what's the picture? I'm working in the Cayley graph of G with respect to some finite generating set. So I'm working in the group with sort of a standard word metric. And I have a hyperbolically embedded subgroup. So here's H. And really what I'm trying to draw here is the vertices in this Cayley graph that are elements of H. But instead of just drawing all the vertices, I'm just drawing it like a blob. And then whenever I take a quasi-geodesic in this space, and the endpoints of the quasi-geodesic are in the subset H, and I take this quasi-geodesic, then that quasi-geodesic is contained in a uniform neighborhood of H. So this property should look familiar from Jacob's talk on the first day. So he defined the notion of a quasi-convex subset of a hyperbolic space. And this was essentially the definition, except it was for geodesics with endpoints on the subset. And in a hyperbolic space, quasi-geodesics are always close to geodesics. So in a hyperbolic space, this would be true for all quasi-geodesics as well. So this property, so defined with quasi-geodesics, is called all kinds of things. Sometimes it's called quasi-convexity. Sometimes it's not called quasi-convexity. I'm going to call it strong quasi-convexity. There is really zero consensus on what to call it, and a lot of people feel very strongly one way or the other. I do not feel particularly strongly, so I chose one. If you would like to argue about it, that is, you could win. Thank you. So some people want to reserve the term quasi-convexity for when you actually talk about geodesics in this space.
Not strongly quasi-convex.
I mean, you could call it anything you want and it would be totally accepted because there's like zero consensus. I think we need some word that like doesn't even involve quasi-convexity. But anyway, I'm calling this strong quasi-convexity. You may see the same property under other names, which is why I'm bringing it up. And this is actually, so this is a generalization of quasi-convexity to spaces that aren't hyperbolic, because the group G here is not necessarily a hyperbolic group. But this is the same kind of geometry as quasi-convex subgroups have in hyperbolic groups. And maybe I'll also say the reason that you want to define this with quasi-geodesics instead of geodesics in this context is because when you define it with quasi-geodesics, it's invariant under quasi-isometry. Right, so this is actually a property of the subgroup and not of the subgroup with respect to this chosen generating set. Right, if it's true for one chosen generating set, it's true for all finite generating sets for the group. So that's why it's defined the way that it is.
So this generating set has nothing to do with one. Like you have the hyperbolic method. Like it doesn't have to do with the relative.
No, that's right, which is why I did not write the relative generating set down. Yeah, if there is some relative generating set, whatever it is, then that hyperbolically embedded subgroup is strongly quasi-convex in the group. So with respect to a finite generating set. Yeah, that's a good point. Yeah. Okay, does that make sense? So kind of a special case of this is when your hyperbolically embedded subgroup is virtually cyclic. So if, for example, you have an acylindrical action on a hyperbolic space, and you have an element of the group that is a loxodromic isometry or loxodromic element, then what this property says, when you apply it to the hyperbolically embedded subgroup that you get from this element, right, that we talked about yesterday, this theorem says that this element G is Morse. So what does it mean to be Morse? It means you are strongly convex, but you're also a cyclic subgroup, right? So this is a cyclic subgroup. It's quasi-isometrically embedded in the Cayley graph gamma GT from being infinite order in this case. And then this theorem says, like this exact this strong quasi-convexity condition is the definition of being Morse. And as was pointed out, as we talked about yesterday, you don't actually have to have an acylindrical action on a hyperbolic space to get this kind of hyperbolically embedded subgroups coming from loxodromic elements. So you could also say that G acts on a hyperbolic space and G in G is a loxodromic WPD element. Then you also get that the element is Morse. So just some examples of Morse elements that you get for this. So if you have any infinite order element in a hyperbolic group is going to be Morse. There, the action on the Cayley graph itself is acylindrical, and all infinite order elements are loxodromic isometries in that action. So this says that they're all Morse. Infinite order elements in a relatively hyperbolic group that are not conjugate into the peripheral subgroup, so not conjugate into H, will be Morse. All of the pseudo-Anosov elements in mapping class groups. In out FN, Jean-Pierre defined irreducible elements. So if you are fully irreducible, which means that you are an irreducible outer automorphism, but also all powers of you are also irreducible, then you are a Morse element. And also, I'll say rank 1 elements in cat zero groups. Okay, so you get a lot of Morseness from these properties. Not all of these are, so these are all immediate consequences of the theorem and corollary. This is not necessarily the first proof that these elements are Morse in some of the cases. For some of these, for example, in mapping class groups, these are exactly the Morse elements. Those are all of the Morse elements that are in the group. Any other element is not Morse. Yeah, that's not true for everything on the list. Yeah. Well, if G is not finitely generated, you have to kind of decide what you mean by this property, right? Because this is a result that's happening in a Cayley graph of G with respect to a finite generating set. So maybe, depending on what you want to say instead. Yeah. It is this property. It's exactly strongly quasi-convexity when the subgroup is cyclic. So like you're looking at so if H is the subgroup generated by G, then any quasi-geodesic with endpoints on that cyclic subgroup generated by the element, that quasi-geodesic stays close to that axis. Other questions? Okay, so for the rest of today's talk, I'm going to assume, so do you remember yesterday I said that if you have an acylindrically hyperbolic group, there is a maximal finite normal subgroup of the group, right? So a finite subgroup, it's normal and it's maximal among all such subgroups with the partial ordering given by inclusion. So for the rest of the talk, I'm going to assume that that finite normal subgroup is trivial. So we denoted that E of G. And this is just because the rest of the results I want to say, when this is not true, you can write down what the right result is, but it just gets a little bit technical in every case. And a lot of the acylindrically hyperbolic groups we care about actually already have this. Many of them do have finite maximal normal subgroup, or sorry, trivial maximal normal subgroup, finite. They have this. Most of them have this. And otherwise, you can take a quotient by E of G and get another acylindrically hyperbolic group, prove whatever you want there, and then just lift it, right, to this finite extension. And it's when you do that lift that statements get complicated, and I don't want to say exactly what happens. Okay, so the first thing I want to talk about is randomness. So hyperbolically embedded subgroups, it's this like kind of weird looking definition, but it turns out that if you take a random subgroup of an acylindrically hyperbolic group, it's going to be hyperbolically embedded. So hyperbolically embedded subgroups are sort of, in some sense, the generic case among finitely generated subgroups of acylindrically hyperbolic groups. So let me tell you what I mean by taking a random subgroup of the group. And I'm just going to say this in the special case and not worry about all the conditions you need on a probability distribution on the group. But I'm going to say that a random walk, actually, instead of saying a random walk. Okay, so the nth step of a random walk on a group, and I'm going to again say that G is generated by some finite set T. This is not required for the general theory, but for like the simple case that I'm going to say, it's easier to have a finitely generated group. So a random walk on a finitely generated group, at the nth step, we denote it W sub n, and it is a word of length n with each of the letters chosen from this finite generating set. And each one is chosen with probability 1 over the size of the generating set. Okay, so this is with a uniform, this is a random walk with respect to the uniform probability distribution on a finitely generated group. You could choose other probability distributions, but I'm basically saying like I'm going to throw all these generators in a bag and I'm going to pull one out at random, and that's going to be the first letter of my word. I'm going to put that back in, shake the bag up, pull one out at random. Here's the second one, and then I'm going to do that n times. So they're chosen independently with respect to the uniform probability distribution. So this probability distribution. Okay, so this is the nth step. You can imagine just doing this more and more times, infinitely many times, and sort of what happens in the limit as you keep doing this, we sort of say that that's like a random property of the group. So we say that a random element of a group G satisfies some property, which I'll just call P, like whatever property you want to put there, infinite order. I don't know why I can't think of another property right now, but like whatever property you can put there. So we say that a random element satisfies property P if the probability that the nth step of a random walk satisfies P approaches 1 as n approaches infinity. So this is what it means for a random element to have a property, right? The more times you pull generators out of the bag, the longer your random word is, the more likely it's going to be that it satisfies whatever property you care about. Okay, yeah. Do you say it again? Yeah, so we'll assume that T is a symmetric generating set. Yeah. Okay, and then, so this is one element. What if we want to form a random subgroup? So a K-generated random subgroup, which I'll call HKN. So it's generated by K independent random walks of length n. So WN1 up to WNK. So K independent random walks of length n. Or I could say the nth step of K independent random walks. Okay. And then again, we're going to say that a random subgroup has a property if HKN has that, the probability that HKN has that property approaches 1 as n approaches infinity. And there's other things you can do. You don't have to have these all be the same length. And then you might want to let their inf of the lengths of the random walks go to infinity. You can change K, so you can have finitely generated random subgroups of different sizes. There's sort of various ways you can change this around. Okay. I knew I was going to get some objections when I wrote it this way, so I was trying to head off. Okay. This is sort of the way that's kind of the simplest to state. Okay, so The theorem, which is due to Marin's system, is that these K-generated random subgroups are hyperbolically embedded. And actually a little bit more. So let G be an acylindrically hyperbolic group. Okay, and again, I'm assuming that the maximal finite normal subgroup is trivial. So for a fixed K, the following hold with probability approaching 1 as n approaches infinity. So the first is that this random K-generated subgroup is quasi-isometrically embedded in G. Okay, so random subgroups are quasi-isometrically embedded in G. When I say G, I mean the Cayley graph of G with respect to that finite generating set T. And this was originally proven by Taylor too, so it was reproven in this paper. Right. The second is that this subgroup HKN is hyperbolically embedded in G with respect to some generating set Y, possibly infinite, where Y is a generating set such that the action of G on the Cayley graph with respect to this random subgroup disjoint, where just G acting on Y is acylindrical. Okay, so random subgroups are hyperbolically embedded, and we can say exactly what the relative generating set is. That part's a little bit less important, but the subgroup is hyperbolically embedded. And the other part is that this random subgroup is free. So it's freely generated by those generators. So Wn1 up to Wnk. So if you take a random subgroup of an acylindrically hyperbolic group, that random subgroup is free and it's hyperbolically embedded and it's quasi-isometrically embedded. Right, so these are pretty actually strong properties, and in some ways it's might be surprising that it's satisfied by a random subgroup.
You're embedded in this G with Y.
Is it QI embedded in G with respect to Y? Yes, it is. Yeah, but it's also QI embedded in the group. Yeah. So the way that a theorem like this is proven is that actually, if you take so I have an acylindrically hyperbolic group. That means that there's some non-elementary action, acylindrical action on a hyperbolic space. It turns out that if I take just one random walk, so just Wn, not K of them, but just one of them, then asymptotically almost surely, so with probability approaching 1 as n approaches infinity, that element is going to be a loxodromic isometry in that action. Right? And in fact, it's going to be a loxodromic isometry whose translation length grows as n grows. So then if you do that K times, you're going to get K different loxodromic isometries. Because you chose the K elements independently, they're actually going to give you independent loxodromic isometries in the action. Lots and lots of details to check behind that one sentence, but you will get independent ones. And so because they'll all have large translation length, if n is big enough, then the ping pong lemma tells you that they generate a free group. So this last part, the fact that it's free is not so difficult to see. The fact that it's hyperbolically embedded uses this characterization of hyperbolically embedded subgroups that I gave you yesterday that says that if you have an action on a hyperbolic space and you have a subgroup, which is QI embedded by the orbit map and geometrically separated, and orbit is geometrically separated, then it's hyperbolically embedded. And the QI embedded by the orbit map kind of comes from the fact that it's being built by these independent loxodromic isometries with large translation lengths. And then the geometric separation is difficult. And that takes kind of a lot of work to get. Does that statement make sense though? So this sort of says hyperbolically embedded subgroups are everywhere, and even free hyperbolically embedded subgroups are everywhere. So sort of inspired by this theorem, Michael Hull and I were interested in what happens if you start with a hyperbolically embedded subgroup and then you take a random walk. So how does that random element, or then you take like a whole random subgroup, how does that random subgroup or that random element interact with the fixed hyperbolically embedded subgroup that you started with? So we show that if H is an infinite proper hyperbolic and hyperbolically embedded subgroup, I guess I could have said that this infinite and proper, that means that it's not a non-degenerate hyperbolically embedded subgroup. So really the extra condition is that it's a hyperbolic group itself. A hyperbolically embedded subgroup of G. Then if you look at the subgroup that's generated by your hyperbolically embedded subgroup and a random walk, and it actually doesn't matter how many you put here, but I'll just put one for simplicity, then this is isomorphic to the free product of your hyperbolically embedded subgroup and the cyclic subgroup generated by that random walk. And this is, that random element is infinite order, asymptotically almost surely. So this is a free product of H with Z. So if you fix a hyperbolically embedded a subgroup, random elements don't interact with it at all. And this subgroup hyperbolically embeds in G. Again, with probability approaching 1 as n approaches infinity.
What could go wrong if H is finite?
No, actually, if H is finite, nothing goes wrong except I guess we don't care. I think, yeah, I don't think there's anything in the proof that's a problem, but typically when we talk about hyperbolically embedded subgroups, then we want non-degenerate ones. So like this new one that you get would be virtually the one you started with. So like you haven't really built something new. It's a good question though. Yeah. What if H is in the center and it's finite? Well, it can't be because G is acylindrically hyperbolic. So it's if it's in the center and it's finite. Oh, yeah, okay. So yeah. Right. I'm not.
Sorry, what if H is, I feel like I'm speaking to some of LM. What if H is finite and it's in the center?
So the center is going to be finite of an acylindrically hyper. I know, and I'm trying to answer your question. If the center of an acylindrically hyperbolic group is finite, and in the case that I'm considering in the statements of these theorems, it's also going to be a normal subgroup. And so I'm assuming it's trivial. So that would mean that the subgroup is trivial. But
someone asked, what if H is finite? And you said, you don't care.
yeah,
I agree with that.
okay, good.
But I'm just supporting the theorem that if H were finite and in the center,
Then it wouldn't be true.
then it wouldn't be true, right?
But what I'm saying is that the assumption I made says that that can never happen, right? So if H were finite and in the center, because of that boxed assumption, H would be trivial, in which case actually it would be true. This E of G contains the center of an acylindrically hyperbolic group, like way up at the top. Yeah. That's not clear from the way I defined E of G, but it is true that the center will be in there. Other questions or objections? Yeah. Okay. Yeah. So this theorem is for fixed K. So they didn't prove it if K grows. I think you could, I think probably if K grew slowly enough, it would still be true. There might be some technicalities, but yeah, I think K could grow. K shouldn't grow faster than N. I think if K and N were growing at the same rate, you might run into some difficulties, but I'm not positive. Mm-hmm. Yeah, that's right. But I think if K grew slowly, then this could be true. Yeah. Yeah.
Can EG equals like a trivial can be crossed in your theorem?
So if EG is not trivial, then you actually, then this isn't the subgroup that you want to look at. You want to look at H times EG and the random walk, and you don't get a free product, you get an amalgamated product over a finite subgroup that's like, I want to say H intersect EG, but I made that assumption, so I didn't write down exactly what it is, but it's like some finite subgroup related to EG.
So you said it's like sub out and thing like the.
Yeah, exactly. This would be true in the quotient, and then you lift it to what happens in the group where E of G is non-trivial. The same thing here. You don't actually get that this is a free group. You get that this is a free group semi-direct product, E of G. And so there's related statements, but just a little bit more complicated.
Thank you.
Yep. Yeah.
So a question about this theorem.
Mhm.
Can you remind why one doesn't imply two? Just confused about why. How different is one and two?
Okay. So if you had an action on a hyperbolic space and you were QI embedded, then you would need another condition, geometric separation, in order to be hyperbolically embedded. But here, actually, the group G is not hyperbolic. So they're pretty, I think they're pretty distinct. So you can have QI embedded subgroups that are not hyperbolically embedded.
Yes, to make it finite.
Yeah. Well, yeah, it's fine. This is finitely generated. I guess, yeah, to say this QI embedded, you do want finitely generated. Otherwise, the statement of QI embedded doesn't make sense. Yeah. QI embedded is about comparing word metrics with respect to finite generating sets, right? So for you to even be able to say it, you need finite generating sets, or for it to be well defined for a subgroup. What is why?
Is it finite?
Typically, no. If it was finite, then the group would be relatively hyperbolic, so you weren't starting with that. But actually what you do is, since it's an acylindrically hyperbolic group, there's some non-elementary action on non-elementary acylindrical action on a hyperbolic space. So choose one of those, and that's why. So you fix the action first, and that gives you the set Y, and then it turns out that this random subgroup is hyperbolically embedded with respect to that generating set. Questions? This theorem is awesome, by the way. I love this theorem. I'm glad you're asking questions about it. Yeah.
The bottom left.
Mhm.
So what will wrong if H is not simply coded? Other cases where.
Oh, yeah, it actually just has to do with the method of proof that we use. So I think it actually should be true for all of them. But what we do is we prove hyperbolic embeddedness by showing that this subgroup is quasi-isometrically embedded and geometrically separated in an acylindrical action on a hyperbolic space. And so we sort of make that assumption for H and then show it's true for this bigger subgroup. I think that actually Michael and I are talking right now about if we can get it for non-hyperbolic, hyperbolically embedded subgroups. But there's a non-probabilistic version that I believe is true. So Francois and I showed that if you take any hyperbolically embedded subgroup of G, then you can find an infinite order element that generates a free product. So this is like a version of the p-naive property. It's not a random, we didn't show a randomness of it, but like you can pick an infinite order element that generates a free product. And we didn't write it down in the paper, but I think that that free product should hyperbolically embed in the group. But there's a difference kind of between, can you find an element so that it works, and does it work for a random element? Yeah, but that's just a factor of our proof.
So maybe just something that makes not paying attention, but physics again with probability one sentence.
Yes, that's right. So all of these hold with probability one, approaching one as n approaches infinity, and the same for this. Yeah. Other questions? I have two more things I want to tell you about, and I'm pretty sure I'm not going to get to both of them, so I'm trying to decide which one I should get to. Okay, so I'm going to talk about, I think the one I'm going to choose is talking about how to use hyperbolically embedded subgroups to simplify problems. So this is like extending properties from hyperbolically embedded subgroups to the entire group. Okay, so I'm saying extensions because you can extend a lot of different things. I'm going to tell you about two of them. The first is about extending actions. So this is joint work with David Hume and Dennis Osen. And so if G is a group and H hyperbolically embeds into G, so we have some hyperbolically embedded subgroup, then given any action, H on some metric space X with no assumptions other than it's an action, maybe a co-bounded action by isometries. There exists an action of the group on some possibly different metric space that extends the action of H on X. And what I mean by extending the action of H is that there exists a coarsely H equivariant quasi-isometric embedding of X into Y. So what you should think, so kind of ignore the word coarsely for now. What you should think is that if you take this action of G on Y and you just restrict it to an action of H, then that restriction looks like the action that you started with, right? If you just look at the orbit of H, that orbit of H looks like the action of H on X. So this is sort of inspired by extending representations, right? So sometimes if you have representations of certain subgroups, you can extend them to representations of the entire group. So it's that same kind of idea here. And the other things that you can say about this extension is that if X is hyperbolic, then you can choose Y to be hyperbolic. Our construction gives a hyperbolic Y. And if the action of H on X is acylindrical, then the action of G on Y is acylindrical. So you can extend actions on hyperbolic spaces to actions on hyperbolic spaces. You can extend acylindrical actions to acylindrical actions. So you can go from actions of the subgroup to actions of the group. And so the other thing is that it's starting with any action, I mean, so co-bounded, but there's really no conditions on this. And in general, if you have a group and a subgroup, this is not true. So for example, every countable group is a subgroup of the symmetric group of the natural numbers, so permutations of the natural numbers. And every action of the symmetric group of the natural numbers on a metric space has bounded orbits. So if you take, and every countable group embeds in it, right? So if you take some countable group that has an action with unbounded orbits, you can't extend that to an action of the symmetric group, right? So this is kind of a special property. It's not enjoyed by a lot of pairs of subgroups and groups.
Yeah, so is it already think of this co-bounded action as an electrification of H?
Yeah, definitely. I mean, maybe not strictly an electrification, but like adding more edges. So with Milner-Schwartz, yeah.
Inducing up that you're describing now. This is so this is X along with coset spaces, some electrified coset.
Yeah, it's exactly that. Like the picture, which actually kind of matches up with the electrification picture. Like, so suppose the action that I wanted to extend were the action on a point, right? And I want to extend the action of a subgroup on a point to the entire group. Like, okay, so I'm going to take my group. H is hyperbolically embedded. So I can look at the Cayley graph of G with whatever this relative generating set is. And then inside here, I see the cosets of H. So I have H, TH, some T prime H, right? I see the cosets. And in general, what I want to do intuitively is take the action of H on X and like glue it on to the cosets, equivariantly onto the cosets. So if H were acting on a point, what would I do? I would take that point, so H is acting just on this point. I would take that point and I would then like attach it to with an edge of length, maybe 1 or something, to every element in H. And then I would do that equivariantly. And this would extend this action. And this is exactly the electrification, right? This is what will be hyperbolic. Now, I don't have to extend the action on a point. So if it wasn't a point, then what I want to do intuitively is H is acting on a space X. Here's my space X, and H is acting on it. So there's an orbit of H in the space. And I like glue the orbit of H in the space to the orbit of H in this Cayley graph. And then the same thing, I do that equivariantly. There's way too many edges there because I did the point and then the space, but that's the general idea. So this space that you get is y. So it's really similar to these electrified spaces, but you're like, you can think of it as only partially electrifying, like you're not going all the way up to a point, but you're crushing it just until you get to X, right? You're crushing H until you get to X. And then, I mean, there's the two bullet points here are the hardest things to show. And there's a lot of technical details going into the fact that when you do this type of construction, when you like shove these spaces X into this Cayley graph, that you don't break hyperbolicity and you don't break acylindricity. And maybe just one application of this. So just one sort of quick thing that you can show if you know that you can extend actions from hyperbolically embedded subgroups to the group, you can show that an acylindrically hyperbolic group admits uncountably many different acylindrical actions on hyperbolic spaces. And all of those uncountably many actions have the same set of loxodromic isometries. So if you hand me an acylindrical action on a hyperbolic space, it's got some set of elements that act as translation in that action. So if you hand me that one, I can hand you back uncountably many more that will be distinct. And I won't have changed the set of loxodromic elements. So I can change just what's going on outside the loxodromics and change the action drastically. So this is joint work with Balasubramanian and Osen. And why is it true? Well, it's true because it's true for the free group. So Ilya Kapovich gave a construction of how to find two actions of the free group satisfying this property. And actually his construction, if you just tweak it a little bit, you can turn two into uncountably many. So we know that we can do this for the free group, and every acylindrically hyperbolic group has a hyperbolically embedded F2. So if it's true for F2, which is a result of Kapovich plus just a little bit more, sort of tweaking his construction. And we wrote this down last time. If G is acylindrically hyperbolic, then there exists an F2 that hyperbolically embeds into G, right? So build these uncountably many actions for F2, extend all of those uncountably many actions to G using this theorem. And then there's a couple things to check that, like, if the actions of F2 were different actions, then the extensions are different actions. But all of those things kind of go through quite easily. And what I mean by different, it means there's no coarsely equivariant quasi-isometry between the spaces. So there's no isometry that coarsely preserves the action. So they're genuinely different. Okay, questions? So one,
5 minutes.
yep, one open problem. My favorite open problem of acylindrically hyperbolic groups, because it seems like we should know the answer and we don't. So it has to do with these loxodromic elements, and you can phrase it in terms of actions, or you can phrase it in terms of hyperbolically embedded subgroups. And let me phrase it in terms of actions first. So suppose that we have two acylindrical actions on hyperbolic spaces. And there are two elements, G and H, in your group. And in this first action, G is loxodromic. And in this second action, H is loxodromic. Does there exist an acylindrical action on a single hyperbolic space such that G and H are both loxodromic? So phrasing this in terms of hyperbolically embedded subgroups, suppose you have two virtually cyclic hyperbolically embedded subgroups, E of G and E of H, and they're hyperbolically embedded with respect to different relative generating sets. Is there a single relative generating set so that they're both hyperbolically embedded there, right? And the problem with something like this is, like, you've got these two hyperbolic spaces, And the idea is like, well, let's put them together and build a new hyperbolic space from them. And there's sort of all the ways that I know to put two hyperbolic spaces together either results in a space that's not hyperbolic, like taking their product, right? Not how to do it. So taking their product, or, you know, taking, well, you can do all kinds of weird things. I've thought a lot of weird ways to put hyperbolic spaces together, but you either end up with something that's not hyperbolic, or you break the acylindricity of the action, right? So the acylindricity and the hyperbolicity are somehow like, they're pulling against each other. And so if you try to fix one, you tend to break the other. I would really like to know if someone can do this, that would be great. Okay, and then the last application that I'm not going to talk about is group theoretic Dane filling. So I decided not to talk about it just in like 10 minutes ago, because Francois did talk about it on Monday for relatively hyperbolic groups. So the theorem that he wrote down on Monday, if you change that the subgroups are like that G is hyperbolic relative to the subgroup H that he was talking about, and you just change it to H is hyperbolically embedded in G, then the exact same thing is true. And the result is not necessarily a relatively hyperbolic group, it's an acylindrically hyperbolic group. So sort of with the natural changes, that same theory holds. And I think I will end with one other open problem, which is probably the biggest open problem in acylindrical hyperbolicity. And that is whether or not being acylindrically hyperbolic is a quasi-isometry invariant. So in other words, and actually we don't even know if it's preserved under finite extensions in general, right? So like any progress towards this would be a really big step. So this says if we have two quasi-isometric groups, you know one of them is acylindrically hyperbolic. Is the other one acylindrically hyperbolic? We don't know. One thing it is true that being relatively hyperbolic is a quasi-isometry invariant. And there you can actually say something more, that if you have a relatively hyperbolic group, so G is hyperbolic relative to H, and G is quasi-isometric to some other group, that other group is not only relatively hyperbolic, but it's hyperbolic relative to a subgroup, which is close to the image of the peripheral subgroup H under the quasi-isometry. So if you take this peripheral subgroup in the relatively hyperbolic structure, push it forward, that's almost a peripheral subgroup in the other group, right? You have to move it a little bit, partly to make it a subgroup. So one possible approach to this is to ask the same question about hyperbolically embedded subgroups. Right? Is there any sense where if you have a hyperbolically embedded subgroup in G, and G is quasi-isometric to some other group, push forward that hyperbolically embedded subgroup under the quasi-isometry, is it still hyperbolically embedded? Can you modify it to get to a hyperbolically embedded subgroup? That's not the only approach to this problem, but that is one approach to this problem. And probably you're going to need to do some kind of modification, and like the image is not going to be it, but you might be able to kind of fiddle around with the image like you do in relatively hyperbolic groups.
Are there any questions?
Yeah.
So, your first question, I mean, suppose you have your loxodromic axis, you can construct these projection complexes, right? So, there's no way to put the two projection complexes together in one projection complex?
I mean, there's certainly may be, I don't know how yeah, I mean, like I don't know how. It's a natural approach, but it's not clear exactly how to do it. But like the point here is that like not only are there just sort of hyperbolic spaces associated, but you can make even nicer, more concrete hyperbolic spaces associated to these elements using quasi-trees, for instance, using Bestvina, Bromberg, and Fujiwara. So like X and Y could be very concrete, but then it's still not obvious how to put them together.
Is there any relation between the Bromov boundary of the two hyperbolic spaces on which G acts acylindrically? Like the G acts acylindrically on two spaces, X and Y. Can you say about Repeat the question.
So the question was, if you have these like loxodromic elements in the two different actions, is there some kind of relationship between the Gromov boundaries? Can you say something about the Gromov boundaries? Not a ton. So, I mean, you know that you get 2 points in the Gromov boundary here that are the limit set and 2 points here that are the limit set. You also know that in the Morse boundary of the group, you have 2 points corresponding to this element and 2 points corresponding to that element because they're Morse. So there's a way to sort of relate in a very restricted sense the Morse boundary of the group to the Gromov boundaries of both of these. But it's not clear where to go from there. One possible approach to this that I couldn't get to work, but other people might be able to get to work, is to build a new space by starting with the boundary here and trying to combine it with the boundary there, right? Like take the join of those boundaries or something, and then like then there are some things you can do, like Bowditch has an annualized system that you can use to then create a hyperbolic space out of something like that. But I couldn't get that type of approach to work, but I think focusing on the boundaries could be a very good way to start thinking about that.
Carolyn again for 3 lectures.
Also, if you think you can solve these, I'm here for the rest of the week. Come talk to me.